Hello, and welcome to the 15th and final webinar in our Lunch, Learn, and Dance Wellness webinar series, Ultraviolet. Joining me in the chat room is Maria Costa and our Manager of Training, Tara Hargraves. Anastasia from Salem Dance Company will lead us in dance beginning at 12:30 Eastern. Let's take a moment to go over the functionality of the Zoom webinar. The audio and video will be from the presenters only. We have found that although you can access the audio through the computer or telephone, the quality of sound tends to be better when listening from a computer. There is a chat feature where people can discuss. If you would like, take a moment now to say hello and where you are from. If you have questions arriving from the content, please enter them under the Q&A section. As the webinar is only a half hour in length and is immediately followed by our dance session, time may not permit for us to answer them during the webinar. The answers will be posted on the website, along with a link to the video recording, a copy of the slides, and a resource document. This can be found under Education Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to the page with that communication. I will also include the topics covered and the length of time spent in the webinar, as some people have requested this to send to the professional association. Lastly, I have automatic closed captioning enabled in the slide presentation. If they are being blocked by your Zoom controls, you should be able to select a different way to view the webinar in Zoom, which makes them easier to see. In this webinar, we will explain what ultraviolet radiation is. We will then look at its uses, both in nature and by humans. We will then go into health concerns and risk factors, along with a word about the UV index. We will finish up with a word about detection, regulation, and protection. We will wrap up with places to find resources on UV protection. Physicists study the interaction of matter and energy. Matter is made of small particles called atoms. All matter has mass and takes up space. Energy is the ability to create change in matter. It has many different forms, but we often talk about two types of energy: kinetic, or the energy an object has due to its movement, and potential, which is stored energy. When energy is transferred out in straight lines, we call it radiation. It can take the form of beams of particles or waves. Electromagnetic radiation is a transfer of energy out from a source in the form of electromagnetic waves or streams of massless and chargeless particles called photons. An electromagnetic wave is the propagation of time-varying electric and magnetic fields in space. In space and in most materials, the fields oscillate at right angles and in phase to each other, as shown in the animation. Electromagnetic waves all travel at the same speed in empty space, called the speed of light. How an electromagnetic wave behaves in material depends on its frequency, wavelength, or photon energy, which are interrelated. If you go from low frequency to high frequency in the spectrum, the wavelengths decrease and the photon energy increases. Ultraviolet radiation is generally considered to be in the wavelength range of 400 to 10 nanometers, or frequencies from 7.5 times 10 to the 14 hertz to 3 times 10 to the 16 hertz. The ultraviolet spectrum is further divided into several ranges. ISO 21348 2007, still in effect, defines UVA as a region from 315 to 400 nanometers, UVB from 280 to 315 nanometers, and UVC from 100 to 280 nanometers, amongst others. The major source of ultraviolet radiation exposure is the sun. Other sources are tanning beds, light bulbs, mainly mercury vapor, but also some halogen, fluorescent, and incandescent bulbs, and some lasers and LEDs, and arc welders. Arc welding produces full spectrum ultraviolet, which is very damaging to the skin and eyes if they are exposed. In order for radiation to affect change in a material, it must interact with it and deposit energy into it. When UV photons interact with matter, they usually transfer energy to electrons, which can cause a few different outcomes. The atom or molecule they are orbiting could vibrate more. More atomic vibration means the material is heated. The photon absorption could cause the electron to move to a higher energy state. Photochemical effects can happen when electrons are moved to higher energy states due to absorption of light. If the photon is very energetic, it can cause the electron to be ejected from the atom to which it is bound, called ionization. Ionizing radiation can break bonds in molecules and is carcinogenic. Ultraviolet radiation is in the range of photon energies where any of these could occur. Because ultraviolet readily interacts with electrons, it tends to deposit its energy over relatively short distances in matter compared to other ionizing radiation, such as X-rays or gamma rays, which even thick layers of dense material like lead may not completely absorb. There are several different photochemical effects which can be triggered by ultraviolet light, which will be mentioned throughout the presentation. Let's start with fluorescence and phosphorescence. Electrons are found in certain energy states around the atom, which are often described as orbitals. They want to be in their lowest energy state, which means as close to the nucleus as possible, but each orbital can only hold so many electrons. When an electron is in a higher energy state than it needs to be, when it drops back down to its lower energy state, it will emit a photon. There are different processes by which this occurs, but two which are quite visible and are related to the absorption of a photon of UV light are fluorescence and phosphorescence. With fluorescence, some of the energy of the photon is dissipated by vibration, so the invisible UV light is converted into a lower energy photon in the visible spectrum. In daylight, pigments which fluoresce seem brighter than others because they reflect the visible light and emit the re-emitted UV light. In the dark, they glow due to the re-emitted light. Phosphorescence is similar, but there is a delay in when the visible light is released. If you have ever charged up a glow-in-the-dark object, the phenomena with which you are working is phosphorescence. Polymers are long molecules with many repeated subunits. They can be natural or man-made or made by human processes. Exposure to ultraviolet light can supply the energy required to form these long molecules and to make linkages between these molecules, called cross-linking. Proteins are tiny structures within our cells that are basically biological nanomachines. One famous example is kinesin, a transport protein shown in the video created by University of California, San Francisco, about Ron Vale, who discovered it. The scientific community has spent and continues to spend resources understanding the nature of proteins. Currently, the Protein Data Bank, a repository of information about proteins, contains almost 180,000 structures. Heat and energy from sources like ultraviolet radiation can change the structure of these proteins, called denaturing. When proteins denature, they no longer work the same way, if at all, which can kill cells to which they belong or alter structures which they support. DNA is also a long molecule. It is found within the nucleus of cells and contains information about cellular replication and protein creation. Ionizing ultraviolet, that is UVB and UVC, can damage DNA directly through ionization. For detailed information on this type of damage, please see the webinar on health effects of exposure to ionizing radiation. Atoms want to be electrically neutral and bond together to form molecules if necessary to achieve this. Orbitals want to have an even number of electrons in them, and these electrons pair up. When ionizing radiation, such as ultraviolet light, knocks electrons out of atoms or molecules, they become charged and no longer have all their electrons paired off. In most cases, this makes them want to bond to other things. We call such atoms or molecules free radicals. They are damaging to living tissue, including their DNA. Ozone, or three oxygen molecules bonded together, is a highly reactive gas which occurs naturally and through human processes which involved electricity or ultraviolet light interacting with oxygen or nitrogen dioxide in the air, or by using electrolytic generators. Ozone is an air pollutant when in the troposphere. the lowest layer of the atmosphere. But the ozone in the stratosphere, located between 15 to 30 kilometers above Earth's surface, plays an important role in protecting life on Earth from ultraviolet radiation from space. It absorbs practically all of the UVC light from the sun, between 90 to 95% of the UVB, and approximately 50 to 65% of the UVA. The effectiveness of its protection is dependent on the thickness of the ozone layer between the sun and the Earth's surface at the place where it is being absorbed. NASA states that without ozone, the sun's intense UV radiation would sterilize the Earth's surface. That sterilization would occur due to protein denaturing and DNA damage. CFCs once caused extreme thinning of the ozone layer, called a hole in the ozone layer, but due to international cooperation, their use has been curtailed and the ozone layer is in much better shape. It is on track to heal completely by the 2030s. The production of vitamin D is a photochemical effect which requires exposure to ultraviolet light. Photosynthesis is also a photochemical effect, but ultraviolet light impedes it. Many living things will fluoresce when exposed to UV light or have structures which are only visible if the eye is able to detect ultraviolet. It is not surprising then that some animals' eyes have evolved to detect ultraviolet light. Ultraviolet light has many commercial and creative uses. Its ability to polymerize and cross-link enables it to cure inks, resins, and bonding agents. These have applications in lithography, jewelry making, in curing nail polish, and in welding plastic. Its ability to damage proteins and other molecules such as DNA in cells is used in sterilization. Fluorescence is used to distinguish true objects from counterfeits. Artists use ultraviolet light in photography and through the use of fluorescent pigments. Ultraviolet light has several medical applications. Once again, its ability to sterilize is useful in a medical setting. It is also used to cure resins, detect previously existing resins, and improve the wettability of implants in dental practices. There are treatments for rickets, psoriasis, eczema, jaundice, lupus vulgaris, and vitiligo, which utilize UV therapy. That being said, the World Health Organization states, despite these important roles in medical applications, the harmful effects of exposure to UV radiation usually far outweigh its benefits, end quote. People with these conditions should consult with their doctor before exposing themselves to sources of ultraviolet radiation. Ultraviolet light has numerous applications in scientific research. Once again, sterilization is a common use. It is also used in analysis of materials such as in astronomy and in mineralogy. Its curing properties are used as well, for example, in microfluidics, where devices that carry liquids on the order of 1,000th of a milliliter are used for research and practical applications. It is also used in biology to image living structures using fluorescent proteins first discovered in jellyfish. Ultraviolet light does not penetrate far into tissues, so it is damaging to the skin and eyes. It does not matter if the source is natural or human-made, deliberate, incidental, or accidental. With respect to skin, it causes premature aging. It damages proteins such as collagen, which leads to wrinkles. UV exposure leads to age spots, the development of moles, and thickening of the skin, amongst other skin changes. For example, this gentleman was a truck driver. The windshield absorbed most of the ultraviolet light because it is made of laminated glass, while the side window, which is made of tempered glass, permitted more UV to enter when up and provided no protection at all when down. With respect to the eye, different frequencies of UV have different penetrating power. Dangers for the cornea include photokeratitis, which is a temporary blindness similar to a sunburn but to the cornea. It is caused by UVB and UVC. The lens of the eye is at risk of cataracts, which are lens opacities or clouding, which require surgery to repair. These are caused by UVB. These effects are called tissue reactions or deterministic. They will occur for certain if the amount of UV light received is over a certain threshold. Pingulaceae are non-cancerous bumps on the eyeball. Pterygium, also called surfer's eye, is a type of bump that can potentially permanently disfigure your eye. These are also caused by ultraviolet exposure. Probably the most concerning health effect from exposure to ultraviolet light is cancer. Cancer is a probabilistic effect, which means that one is not guaranteed to get cancer if exposed to something known to cause cancer, but the risk of getting cancer is increased with exposure. Exposure to ultraviolet B and C, because they are ionizing, can cause cancer by changing DNA, which affects how cells reproduce. This happens through direct ionization of DNA or the production of free radicals. Exposure to UVA is also carcinogenic, although it is not ionizing. It does this through oxidation, a type of chemical reaction, and by damaging DNA repair proteins. The IARC monographs on the identification of carcinogenic hazards to humans classifies UV radiation as group 1, which means it is carcinogenic to humans. The skin has several layers. The depth of penetration of ultraviolet light depends upon how much it interacts with the electrons in the skin. UVC, which would only be encountered from human-made devices due to the ozone layer filtering it out, penetrates the least, only reaching the epidermis. UVB can penetrate the upper layer of the dermis. UVA light can penetrate well into the dermis. When the skin is reddened from exposure to UV light, it is a sign that it has penetrated the epidermis and is damaging the tissues below. Tanning is an attempt by the body to protect itself from the damaging effects of ultraviolet light. Developed in 1975 by Harvard Medical School dermatologist Thomas Fitzpatrick, MD, PhD, the Fitzpatrick scale is used by the medical community to categorize various skin types and their susceptibility to UV light. The World Health Organization states, due to their relative lack of skin pigmentation, Caucasian populations generally have a much higher risk of getting non-melanoma or melanoma skin cancers than dark-skinned populations. Naturally brown and black people, skin types 5 and 6, can usually safely tolerate relatively high levels of sun exposure without getting sunburnt or greatly increasing their skin cancer risk. In contrast, people with pale or freckled skin, fair or red hair, and blue eyes belong to the highest risk group, skin types 1 and 2. People with dark hair and eyes who do not normally get sunburnt are at medium risk of developing skin cancer, skin types 3 and 4. Nevertheless, excessive exposure to intense sunlight can damage all skin types. The risk of eye damage and heat stroke is the same for everyone, end quote. We are now going to discuss precancerous and cancerous lesions caused by exposure to ultraviolet radiation. I apologize in advance that some images may be difficult to look at. Information on the following slides outlining precancerous conditions and cancer of the skin is based on information from the Canadian Cancer Society. Images are from other locations and author attributions are given. Actinic keratosis is precancerous condition of the skin, which may also be called solar keratosis. Precancerous means that the tissue has changed so that they are more likely to become cancer. If actinic keratosis is not treated, it is likely to develop into a skin cancer called squamous cell carcinoma. It often appears as small, rough patches that feel like sandpaper. They can get bigger and turn red or brown. They may be itchy or burn. There may be many patches together in one area. There is usually more than one area of actinic keratosis. There are three main types of skin cancer: basal cell carcinoma, squamous cell carcinoma, and melanoma. Basal cell carcinoma starts in the round cells called basal cells found in the top layer of the skin, called the epidermis. It makes up about 75 to 80% of all skin cancers. It tends to grow slowly and rarely spreads to other parts of the body. It may grow into nearby tissues if left untreated. The most common sites for basal cell carcinoma are the head, face, and neck. Shown is an image of superficial basal cell carcinoma, which is one of four types: nodular, superficial, infiltrative and micronodule, and morphiform. Squamous cell carcinoma occurs in the squamous cells of the skin. They are flat cells located in the outer part of the epidermis. Squamous cell carcinoma is the second most common type of skin cancer, accounting for about 20% of all skin cancers. It usually grows slowly, but more quickly than basal cell carcinoma. It is more likely than basal cell carcinoma to penetrate other tissues and spread to other locations in the body. If found early, it is not usually life-threatening. Two subtypes which have a high risk of recurrence are desmoplastic squamous cell carcinoma and adenosquamous carcinoma. Keratoacanthoma looks like squamous cell carcinoma. It can undergo spontaneous regression, which is spontaneous shrinking in weeks or months. It is sometimes considered a variant of squamous cell carcinoma. Melanoma is less common than basal cell and squamous cell carcinomas, but can be very concerning. It begins in melanocyte cells, which produce melanin, which in turn gives our skin, hair, and eyes color. Melanocyte cells can group together to form moles, most of which are non-cancerous. But if the melanocyte cell becomes melanoma, they can grow into and destroy other tissue and spread to other parts of the body. When not caught early, melanoma can have a poor prognosis. There are four main types of melanoma, namely superficial spreading, nodular, lentigo maligna, and acra lentiginous. The ABCDE rule below can help you look for the common signs and symptoms of melanoma skin cancer. See your doctor if you have any of these changes on your skin. A is for asymmetry. One half of a mole does not have the same shape as the other half. B is for border. The edge of the mole is uneven or irregular. It can look jagged, notched, or blurry. The color may spread into the area around the mole. C is for color. The color of a mole is not the same throughout. It could have shades of tan, brown, or black. Sometimes areas of blue, gray, red, pink, or white are also seen. D is for diameter. The size of a mole is larger than 6 millimeters or 1/4 of an inch across, which is about the size of a pencil eraser. E is for evolving. There is a change in the color, size, shape, or feel of the mole. The mole may become itchy, or you may have a burning or tingling feeling. Other signs and symptoms of melanoma skin cancer include an area that does not heal, a mole or sore that oozes or bleeds, a broken skin with an open wound, or ulceration. Besides basal cell carcinoma and squamous cell carcinoma, there are a number of rare non-melanoma skin cancers. They make up about 1% of all skin cancers. Merkel cell carcinoma is shown. Did you know that eyes can get moles? As with moles in the skin, some moles in the eye can develop into melanoma. Canada has adopted the use of the UV index developed to help people protect themselves from the sun's damaging UV rays. The higher the UV index, the stronger the sun's rays. In Canada, the UV index ranges from 0 to 11 plus. From the Government of Canada website, the UV index scale ranges from a low of 0 to a high of 11 plus in Canada. The highest values occur in Southern Ontario, where values of 11 or even 12 on rare occasions have occurred. The sun's rays become stronger as you move south, and in the tropics, the index can rise to 14 or higher. The UV index values are grouped into 5 levels of risk: low, 0 to 2, moderate, which is 3 to 5, high, which is 6 to 7, very high, which is 8 to 10, and extreme, which is 11 plus. The numbers on the scale indicate the strength of the sun's UV rays. The higher the number, the stronger the sun, and the greater the need to take precautions. The UV index was created in 1992 by scientists at Environment and Climate Change Canada as a tool to help protect Canadians from overexposure to the sun. The scientists set the original UV index scale from 0 to 10 based on the UV values usually found in Canada. In 1994, the World Health Organization, or WHO, and the United Nations Environmental Program recognized the value of the UV index and adopted it as an international program. Just as with other forms of electromagnetic radiation, there are instruments and dosimeters which can detect ultraviolet radiation. That being said, they are not common in workplaces where people are exposed to ultraviolet light. There are numerous regulations in Canada related to ultraviolet light, many with respect to the use of tanning equipment. Tanning beds are of particular concern with youth and young people because they are being exposed to high levels of carcinogenic radiation, and they are more susceptible to its effects due to the fact that their bodies are still growing. Tans can also give people a false sense of security as they think it protects them from UV, but it only gives a very low sun protection factor. Sun protection factor, or SPF, is an indication of how long one can be exposed to the sun's UVB rays with minimal damage compared to having no sunscreen at all. SPF 30 means it will take 30 times as long for skin to redden. There are no occupational exposure limits for ultraviolet radiation federally in Canada. Exposure falls under the jurisdiction of the provinces and territories as part of the Occupational Health and Safety Acts or the Canada Labour Code for federally regulated workplaces. The American Conference of Governmental Industrial Hygienists, or ACGIH, has recommendations which are adopted in many jurisdictions around the world. These are found in the publication Threshold Limit Values for Chemical Substances and Physical Agents and Biological Exposure Indices. So what can we do to protect ourselves? Well, first is to stay in the shade, especially when the sunlight is strongest. You can follow the UV index to help with this and know that it is strongest in the middle of the day. Even when there are clouds, some UV might get through. You can wear clothing that blocks the sun. Be aware that UV can get through thin materials. Your clothing should include covering for your arms and legs, as well as a hat to shade your face. Wear sunglasses with SPF to protect your eyes. Your pupils naturally dilate when you wear sunglasses, so if they do not have UV blocking capabilities, more UV will enter your eyes than if you do not have them. Replace sunglasses if they become cracked or any protective coating is scratched for the same reason. You want to apply a broad spectrum sunscreen or SPF 15 or higher, following the directions for reapplication on the bottle. If you are spending a lot of time in UV light, you want to use SPF 30. It was once thought that only UVB did damage, that now that the dangers of UVA are known, broad spectrum is important. This is important not only in the sun, but when exposed at work or in the nail salon, for example. Tanning beds cause skin cancer and other effects previously mentioned. To prevent this, do not use them. Young children are particularly at risk for damage from UV light, so make sure they're protected as well. The best measure is to avoid sun exposure as much as possible. There are a number of concerns online people have about sunscreens. According to Harvard Health, there is no conclusive evidence that sunscreens adversely impact health. They provide protection against all 3 common skin cancers. Sunscreen does block vitamin D production. There is a debate in the medical community as to whether or not sunscreen should be applied after 10 to 15 minutes of sun exposure each day. Some doctors feel this is a good idea, while others feel that this is not justification not to wear sunscreen because the risks of harm are so high and supplementation is available. It has been recently shown that certain ingredients in sunscreens are harmful to marine life, especially corals. The National Ocean Service recommends that if you are going swimming in areas with sensitive marine life, consider sunscreen without chemicals that harm them. Seek shade between 10 a.m. and 2 p.m. and use ultraviolet protection factor swimwear. There are numerous resources available with information about the effects of ultraviolet radiation on health. In the follow-up mailing, I will include a link to a compilation of materials available from our site and those of Health Canada, the Infrastructure Health and Safety Association, or IHSA, the Canadian Cancer Society, the Canadian Skin Cancer Foundation, Carex Canada, the Canadian Centre for Occupational Health and Safety, or CCOHS, Sun Safety at Work, and the World Health Organization. We hope you found this webinar on ultraviolet light informative. If you have questions about radiation or any other radiation safety topic, please feel free to contact us at the Radiation Safety Institute of Canada. We have a toll-free information service to support questions from employers, workers, and the public with respect to both ionizing and non-ionizing radiation safety. We also provide consulting services for those who might need support in developing a radiation protection program and related services, including radiation surveys. If you have any further questions about ionizing or non-ionizing radiation, please feel free to contact us toll-free at 1-800-263-5803 or by email at info@radiationsafety.ca. You can also visit us on the web at www.radiationsafety.ca or find us on Facebook.